Okay, so we've got three things to cover today. The first thing is a little bit of notation and terminology. In other words, a definition of a Reimann sum. We're going to talk a little bit about what a definite integral is, and then we're going to end with some geometry. And so it should be, hopefully, pretty straightforward. The first thing is a little intimidating after we get past the objective. So we're going to talk about a Reimann sum. Reimann, famous mathematician, invented the Reimann sum. We're going to talk about what a definite integral is, because we've done indefinite integrals, so now we want to do definite integrals. And then we're going to talk about those definite integrals and some properties, which you'll already have a pretty firm grasp of. And then we're going to use some mad geometry skills to bust out some calculus. All right, Reimann sum. So Riemann's a mathematician guy that based his stuff off of the earlier lessons from Leibniz and Newton. And he came up with an idea that I'll get to in a second. But let's talk about this terminology. This is the fancy terminology they use. And that is what's called a Reimann sum. The Reimann sum is the sum of all the rectangles, which is what you've been doing already. The difference is that Reimann asked a simple question. Why do all these rectangles have to be the same width? Can't we just change the width of the rectangles to get a better answer? And so he came up with this notation. And what's the sigma do, by the way? I'm sorry? Adds everything up. So the notation here is delta x is the width of one rectangle. Okay, so again, that's, we talked about the delta x yesterday. F of ci is the height of one rectangle. So what that means is, that's the same thing that we did when we did f of 1, f of 2, f of 2.5. But we're taking some general point, c sub I, where c is the number between a and b in our range. And then the sigma will add all those things up. I is 1, that's our first region, n is the number of regions that we have. So you always start with 1 and you end with the number of rectangles you have. So it's just a fancy way of saying add up all those rectangles. Are we good? Just so you see that notation, I want you to understand what it's saying. Okay, this is base times height, area of a rectangle, and then the summation symbol then says add up all those base times heights. Bases times heights, whatever it is. Okay, so then again, Reimann said, well, what if they're not the same width? So he introduced some new terminology. He said that, there's a picture of different widths, great. Okay, he said we don't have a delta x anymore because delta x changes from rectangle to rectangle. So he introduced this notation here. He called them partitions. And what he was concerned about is the biggest partition. So if I go back a picture, I've got yellow, light blue, green, and red. And what he was most concerned about is the biggest rectangle there. I should say the widest rectangle in that picture, which would be the green one. He didn't care about the yellow, the blue, and the red. And you'll see why in a second. He called that, by the way, the norm of the partition. There's the notation. It's like a double absolute value bar of delta.
What is that?
That's the width of the largest, or the fattest rectangle.
So, wait, does it have to be the fattest one?
It's got to be the fattest one, and you'll see why in a second. Okay. He doesn't care about all the little guys, just the big fish. We talked about this already. How do we get the most accurate answer? In other words, how do I cut down on the wasted space? We said we had two options. One was add more rectangles or make them smaller. Okay, so Reimann chose the approach of let's make them smaller. If we have all the same rectangles as delta x, then we just need to shrink delta x down to 0. What Reimann said is, wait a second, I don't have the same width of rectangles, so I'm just going to take the fattest one. If I can get the fattest one to shrink down as small as possible, then the skinnier ones will shrink down also. Does that concept make sense? Let's shrink the biggest one down to 0, and in the process, all the other ones will shrink down to 0, which is what he did here. So we've got this limit notation. We're going to take the fattest rectangle, we're going to shrink it down to 0. If we shrink the width of the fattest rectangle down to 0, then the number of rectangles is going to go up, and we'll get as accurate an answer as possible. Okay, so this is just some concept things that I want you to be able to talk about in a fairly intelligent way. So there's some terminology that you should know. What is a partition? What is a norm? What's the notation to represent each of those things. Okay, and then the big thing is the concept, and you already have the concept that we want the width of the rectangles to be very skinny, or we want the number of the rectangles to get very large. Okay, that's eventually what we're going to do, and when you do that, you get what's called a definite integral. When we were doing indefinite integrals, we didn't get numerical values, we got equations. Definite integrals are going to give you numerical values. And what does that numerical value represent? Cricket, cricket. What's the physical representation of the integral? Area
Under the curve.
area under the curve. So this is going to give us an actual numerical value for that area under the curve. We were talking about breaking it into rectangles and doing that, but eventually we'll get to something called a definite integral, which will allow us to do that. Okay, so some notation here. We take Reimann Sum, or his fancy artsy-fartsy way of writing this, the calculus speak, and we turn it into something a little bit easier for us to understand. You've seen this before. We got the squiggly integral symbol. There's a difference, though. We've got an a and a b up on top. We did indefinite integrals with no numbers up on top, which means we took the integral of x squared and said, if I take the indefinite integral of x squared, I'll get 1/3 x cubed. So I took a function and got another function. This is saying, no, I want the area under the curve from a to b. A is our starting point, b is our ending point. Fancy calculus speak is upper limit and lower limit. Where do you start? Lower limit. Where do you end? Upper limit. So from here we're going to do two things. We're going to talk about some properties, and the properties aren't that difficult because we've actually been using those properties already. And then we're going to do some geometry. After I give you a second to write all that down. Okay, we good? Nope, but okay. Now we're good? Okay. So these properties are pretty much repetitious to what we used with derivatives. So for instance, the integral of a sum is the sum of the integrals. The integral of a difference is the difference of the integrals. You know that already. We used that when we did derivatives also. Move the constant out in front. Done that a ton. So instead of taking the antiderivative of 3x squared, you're actually going to take the integral of x squared and then multiply your answer by 3. If you go from a to a, the integral is 0. Why? If I take the definite integral from some number a to that same number, why is the answer 0?
Because if you multiply by a width of 0, you get 0.
Yeah, how wide's my rectangle there?
0.
0. Does everybody see that? That's an important concept that's going to pop up a lot. For those of you that are visual learners, I'll draw you a picture. We have some function. And normally what we would do is we would go from a to b and calculate the area under the curve, because again, the physical representation of the integral is the area under the curve. What this bottom one is saying is now slide b over there and find the area under the curve from a to a. No rectangle. Or it's a rectangle with 0 width. Therefore, the area under the curve would be a segment which has a width of 0. That pops up a lot. We good so far? Yeah, good. Oops, wrong way. Okay, another concept that probably requires a picture is that if we're going to go from A to B, we can split it into two different regions. Whoops. Yeah, I think that worked. So here's A, here's B. All right, that's the first integral here. But it says that if I take a point C somewhere between A and B, let's put C here, I can break this into two regions. Here's one region, here's the other region. Okay, does that make sense? This is the important part. C has to be between A and B, otherwise it doesn't work. So instead of going from 2 to 5, I can go from 2 to 4, and then from 4 to 5. And then the last one that's fairly important. We always want the number up on top to be the bigger of the two numbers, because we want to go from the lower number to the bigger number. But what if it isn't? You can switch these as long as you put a minus sign in front of it. So from going from 2 to 7 is the same thing as going from 7 to 2 as long as you multiply by a negative number. And you'll see that. They'll ask you for the integral from 2 to 5, which makes no sense. We want to switch that because we want the bigger one up on top. So you just switch them as long as you multiply by a negative. Okay, so some given information. We're going to use this to solve the following problem. The integral from 4 to 2 of x cubed dx is 60. The integral from 4 to 2 of x dx is 6. And the integral of dx is from 4 to 2 is 2. We don't care where those numbers came from because that's just given information. I want to use that to find this. So applying the properties, I'm going to split these into a whole bunch of different integrals and solve it from there. So in other words, I can apply the summation formula and break it into 3 separate integrals, separated by the plus and the minus. Then I can move the 10 out in front, move the 4 out in front, move the negative 3 out in front, and then I gave you each of these 3 things. Plug and chug and you get that. What about that negative number? Anybody bothered by that? No? We're okay with a negative answer?
Can you go over that
Yeah.
solution again?
Yeah.
How I got this solution?
Like what you even did.
Okay, so one of the properties is the integral of a summation or a difference. I can split into 3 separate integrals with that. Okay, so you good there? What I also did is I said, well, if I have a constant times a function, I can just move the constant out in front. So I moved the constant out in front here. I took the 4 and moved it out in front, and then moved the negative 3 out in front. Then each of these 3 things, that, and that, I gave you up here. So I just plugged and chugged. Right now, we don't need to know how to calculate what that value is. That's why I gave it to you as given information. So it's just an application of the properties. So again, since there's a big red balloon on it, we probably want to address the fact that should be bothersome. Why? What does that number represent? Area. Have you ever seen a negative area before? No. Is it wrong? No, that is correct. So now in calculus, we get introduced to this weird concept. And the weird concept is that we can have something that's going to generate a negative area. Okay, which, again, doesn't make much sense when you take a geometric approach to it, but from a calculus standpoint, it works fine. There's a simple explanation for it, which is on the next slide. Are you good with this one? Okay. And there's the explanation. Any part of a curve that ends up below the x-axis becomes a negative area. That's just how it's defined. And you'll see why it becomes negative when we start doing actual definite integral calculations. But for now, you just need to remember that anything below the x-axis is going to be negative. It doesn't have to be on the left side of the y-axis. It can be wherever you want. But anything below the x-axis is going to give you a negative area. So if a majority of your graph is below the x-axis, you will get an overall answer of a negative area. Like this problem. And we can estimate the rectangles, but you can see that this area is bigger than that area, so your overall answer here will be negative. Okay? Problems? All right, let's do some geometry. A couple of review things. You should know those. Well, you should know the top two. You may have forgotten the bottom two. If you don't know any of those, write them down because you're going to use them. If you can find the area of a circle, area of a rectangle, area of a triangle, and area of a trapezoid, and you don't even have to be able to find the area of a trapezoid because you can break a trapezoid into a rectangle and a triangle if you prefer, you can do the following work.
How do you call it trapezoid?
Because that's how it's pronounced. How else would you pronounce it?
Trapezoid?
No, that's an E, not an A. Trapezoid.
It's pronounced milk, but some people say milk.
Why would you say milk? It's not spelled
No, people
M-E-L-K.
do.
Who says milk?
But I have a question, Mr. Ryan.
Egg and egg.
Yeah.
Egg
Yes,
and
Green.
Do you call it an egg
Green's
or an
novel.
egg?
Knobbly. Go what?
Do you call it an egg or an egg?
Egg.
It's always an egg.
How about that dog-looking thing that runs through the woods? No, dog-looking thing.
A wolf?
A wolf. You ever heard anybody call it a wolf?
Yeah.
Yes.
It's another one.
Yeah, I've heard
Wolf.
someone say
I was
wolf.
attacked by a wolf.
Yeah.
A what?
Dog.
Oh yeah. You've all heard that, right?
Yeah.
Okay. No, you've never heard anybody call it a wolf?
No.
Oh yeah.
I haven't heard anything.
I heard somebody say. Someone
How about
says wolf.
Isosceles?
Isosceles.
You also say parabola.
Parabola.
What is it?
Parabola. Parabola, isosceles, and trapezoids. Anyways, okay, so we want to find, we're going to solve three problems here. We're going to find the area under the curve from 1 to 3 of the function 4. That'll be fun. We'll find the area under the curve of the function x plus 2 from 0 to 3. And then we'll find the area under the curve of the square root of 4 minus x squared. All of this requires no calculus. It's all geometry. Or geometry, if you prefer. I put the syllable in the wrong place. What's the graph of 4 look like?
M5.
Point? Line? I don't know. Is it? Line? Line. Anybody else? What's the graph of 4 look like? It's a line. What kind of line? A straight line. Good, because all lines are straight. It's like saying a round circle.
I know. That's what I was like.
Right.
I don't really know what's going on. I have no idea. I really
But you contributed, and that's really all we're looking for. Good job. Class participation points.
Vertical line?
I'm sorry?
Vertical line?
No, it's a horizontal line. Y equals 4 is a horizontal line.
I thought it was that.
No, it's a function. Hold on, before I click on the next slide, let's make sure we got this under control. Y equals 4
Yes, I get
Or is
the
it one line?
is a horizontal line
At 4. Yes, I get it.
through 4. And we want to find the area under the curve from 1 to 3. What are we looking for the area of?
No, rectangle.
It's a rectangle, good. How wide is that rectangle? How tall is that rectangle? Therefore, this should be equal to 8. Good.
So that's the answer?
This is gonna go downhill quick.
That's
Yeah. That's it. That's all you have to do. It's just geometry.
So you're drawing?
You're drawing, right. We're making drawings.
All right, Michael Caine.
Oh, yeah. You just call me Alfred. Second one was what? X plus, I don't know why I'm yelling at you. X plus 2. What does the graph of x plus 2 look like?
Is it through a straight line? No, what is that?
Say again?
Is it straight line?
It's 3, 0.
Oh, for, no, it's from 0 to 3.
0 to 3?
For the next one, yes, 0 to 3. So what's the graph of x plus 2 look like?
It's y equals x shifted up 2.
Y equals x shifted up 2. Has a y-intercept of 2, has a slope of 1.
Yeah.
Looks like that.
Yeah.
And we're going from 0 to 3. We want to find the pink region. So that region is a trapezoid. If you're not good with trapezoids, then break it into shapes that you can work with. So for instance, you might want to split this trapezoid into a triangle and a rectangle. I did it as a trapezoid. So this is the height. This is base 1, this is base 2, plug and chug. If you break it into a triangle and a rectangle, this is 3, this is 2. So 3 times 2 is 6 divided by 2 makes that an area of 3. And this is a rectangle that's 3 by 2, which is 6. And 3 plus 6 is, uh-oh.
The height is 3 of the triangle.
Oh, it goes up to 5. Sorry, I was at a weird angle.
So is Emma.
Yeah.
Is that better?
Wait, Mr. Eddie,
Yeah, that's better. Because 10, yeah. Huh?
how'd you get 2 and 5 to the trapezoid? Or from-
This is base 1. This is base 2.
Oh, okay.
So again, use whatever method you want. All right, next problem. The square root of 4 minus x squared. What does that look like?
Isn't it just
Minus 4.
upside down?
Nope. Is it minus x squared?
I don't have it.
Is it minus or plus? Yeah, minus x squared. Yeah.
2
Nope.
No, just kidding. That was a lie.
Yeah. That's one of the things you should know. It's a semicircle with a radius of 2. Upper half of a circle, also known as a semicircle, radius of 2. So we want the area of a semicircle, which would be half the area of a circle.
So we have to know how to.
You don't have to do anything, Casey. It's American.
You do have to know how to graph that.
No, you don't. No, you don't.
If you want to do this problem.
Well, that's a conditional that wasn't initially stated in the argument.
I just think
2 pi.
2 squared. So that's
Okay, you ready to put it all together?
the.
Yeah. No?
Let's put it down now.
Yeah.
Oh, wait.
What? Oh, I gotta go back.
Oh, that's question. Gotta go fast.
Alright, we're good.
We still do not know how to take the derivative of the absolute value of x, let alone take the integral of the absolute value of x. So we're going to cheat by drawing a picture. Here's the absolute value of x. It's the V looking thing. I want to find the area under the curve from -3 to 2. -3 to 2. The area under the curve would then be these 2 little triangles. Like it says, think about it graphically. Draw a picture. Find the area of the 2 triangles, add them up, you get your area. So we don't care how to find the antiderivative of the absolute value of x, because I can draw a picture. And you should be able to draw a picture also. Needle point thread.
How'd you get 4.5?
4 no's on that. How to get what?
4.5.
Shh, battery's low. Darn it.
That's
How do you
the
say
area of
that?
1 plus the area of the.
You have your calculator handy too? Can I borrow it for a
Oh,
minute?
so you break it?
No, I'm just kidding. I was gonna steal a battery from you. I couldn't be that close. I'll do it for you.
No, I heard that. Can you answer my question?
Heard what?
Can you tell me how to get 4.5 and 2?
The area of the triangle.
3 times 3 divided by 2, because it's French week. 4.5. 2 times 2 divided by dos.
Wait, I still don't understand why you do that.
How's the other one?
Because the area of a triangle. 1/2 base times height. All the what? What?
Have it on
It's like mismatch.
there. Beautiful day.
We saw that.
Let's go back for a second, and since you guys have a pretty firm grasp of this, let's do the same problem. But let's do this. This will be fun.
It would be fun.
Tap it out.
Move it up too.
Okay, so we move it up 2. Same answer?
Yeah.
Shape didn't change.
He was being sarcastic.
It's longer, right?
Yes.
Oh.
Move it up to.
Negative
Just move it up
2.
to.
Is that the same?
Just move it up 2.
Just move it up.
Same answer?
Yeah.
Yeah, shape didn't change, right?
No.
How do we define the integral? Area under the curve.
Oh.
Right? No problem? Uh-oh. What about this stuff? Who cares? Great. This rectangle's overrated. We don't care. How big's that rectangle?
4 by 2.
4 by 2 plus 2 pi. So the answer to this problem would be 2 pi plus 8.
Mr. Reed.
Because, hold on, let me finish my diatribe here. When you move it up, when you shift it up or down, you have to consider the distance from the curve down to the x-axis, not just under the curve. What if we flip that over? What if we want to find the area under the curve of this guy?
You do a rectangle and subtract the circle. Half circle.
Hot diggity. Take the rectangle and subtract the semicircle.
Swag.
Pretty cloud. Yes, Grant?
Alright, looking at the homework, how would you do an upside down parabola?
How would you do an upside down, you sure it's an upside down parabola?
25 minus x squared.
25 minus x squared is an upside down parabola that's been shifted up 25 units.
Yes.
Do they give you any information in the problem?
Is this not word
You just gotta set up a definite interval.
Oh, set it up. Yeah, not solve it.
Oh.
So you just got.
You gotta get your squiggly involved, you gotta know your limits of integration. These, by the way, are called limits of integration.
Oh, so I was.
No, upper limit, lower limit. This is fun.
How do you do it?
We good?
Yeah.
Yeah! Oh, I don't know where that came from.
It's all standard.
Standard form if you wanted to review that. Okay.
That's like John Travolta.
Those are mismatched.
Yeah. Yeah.